All right, let's just jump right into one of the most mind-bending ideas in all of physics. We're going to talk about how the universe, at its most fundamental level, might be completely timeless. And yet, somehow, that timelessness is exactly what creates the reality you and I experience every single moment.
It all kicks off with a question that sounds so simple, you almost feel silly asking it. Why can you remember what you had for breakfast yesterday, but you have no idea what you'll have for breakfast tomorrow? The answer seems obvious, right? I mean, come on, one already happened and the other hasn't yet. But what if I told you that from the perspective of deep physics, that's not obvious at all? In fact, it's a huge mystery.
Yeah, here's the kicker. When you get down to the quantum level, the actual rules that run the universe, they don't care about the direction of time. The math works just as perfectly forwards as it does backwards. So that one-way street we all feel we're on, that's not a fundamental law of nature. It's something that has to be created, and we're about to figure out how.
So to really get this, we've got to look at the two very different, kind of contradictory ways that physics thinks about time.
On the one hand, you've got classical time. This is our world. This is the time of everyday life. It's a one-way street, no turning back. You can't unscramble an egg. Disorder, or what scientists call entropy, is always increasing. But then, you zoom all the way down to the quantum world, and it's a totally different story. Down there, everything is reversible. Quantum systems can evolve forwards or backwards in time without any preference. So, how do we get from that two-way superhighway to our one-way street?
So how do we get this arrow of time? Well, it isn't just a given, it has to be made. And for it to emerge, you need a very specific two-ingredient recipe. First, you need a very special starting condition for the universe, a state that was incredibly ordered or low entropy. And second, you need a process called decoherence to step in and break that perfect time-symmetric quantum world. And decoherence, well, it all comes down to one thing. And that one thing is entanglement. It's not just some weird, spooky action at a distance. It's literally the glue that holds the entire universe together.
Okay, now this is a huge distinction. It's not just one kind of entanglement. You can think of it as two flavors. First, there's coherent entanglement. This is the pure, perfect stuff. It preserves all the quantum information, and this is what actually stitches the fabric of space together. Within these systems, time is still that two-way street. But then you have decoherent entanglement. This is what happens when a quantum system gets messy, when it interacts with its environment. Information leaks out, entropy goes up, and this is what kicks the arrow of time into motion for us.
Yeah, this quote really says it all. The fundamental structure of our reality, of space itself, is built out of these perfect, coherent quantum connections.
So here's the thing. Reality isn't one or the other, it's both at the same time. The universe, as one giant system, can stay perfectly coherent and timeless. But down here, where we live, in our little local patch, things are constantly interacting and getting messy. That local decoherence is what creates the irreversible flow of time that we all experience.
All right, so how does this all actually work? What's the mechanism? Well, a really fascinating framework for this is called Constraint-Resonance Emergence Theory, or just CRET for short. CRET basically says reality is built like a three-layer cake, from the bottom up. At the very base, the T layer, you got these tiny pixels of reality, Planck-scale bits of quantum information. Then those pixels get entangled with each other, and that process stitches together the next layer, the C layer. That's the actual fabric of spacetime. And then governing the whole thing from the top down is the lambda layer, the big overarching laws of physics, like geometry and thermodynamics. This whole system builds itself in what's called a resonance loop. It starts by going upwards. All that tiny entanglement happening at the pixel level gets amplified, scaling up and up until, boom, it creates the large-scale geometry of spacetime. But, and this is the really cool part, it's not a one-way street. That big structure that just got created then pushes back down. It acts like a filter, basically telling the pixels which of their entanglement patterns are stable and allowed to exist and which ones aren't. This constant back and forth, this resonance, is what CRET says creates a stable reality. So what's doing the filtering? What's the ultimate rulebook that's keeping this whole loop in check? Well, this brings us to the absolute core idea we're talking about today, the real role of the wave function. We usually get taught that the wave function is just a math tool, for calculating the odds of where a particle might be. But Siertz says, no, it is so much more than that.
It's a real physical constraint on reality. It's the shared rulebook, the literal sheet music, that every single entangled particle in a system has to follow, all at the same time. I absolutely love this analogy. Think of reality as a grand orchestra. The particles, they're the musicians. The wave function, that's the sheet music they're all reading from. Coherent entanglement is when they all play their parts perfectly, creating a beautiful harmony. And decoherence, that's the random coughs and chair scrapes from the audience, the environmental noise that makes things a little messy and creates the forward march of the song. And this sheet music, this constraint, is absolutely critical. It's the only thing that keeps the whole system viable. Without that shared rulebook, the orchestra just dissolves into a chaotic mess of random noise. The wave function is what prevents reality itself from just falling apart. So let's take this incredible idea and scale it all the way up. I mean, all the way. If a system of particles has a single wave function, what about the wave function for everything? Well, it exists. It's called the Wheeler-DeWitt equation, and it is wild. The most profound and baffling thing about it is that little equals 0 at the end. There's no t for time anywhere in the equation. This implies that the universe, when you look at it as one single gigantic quantum system, is fundamentally timeless. It doesn't evolve. It just is.
So wait a minute. How can the universe be timeless if I'm sitting here and my watch is clearly ticking forward? This is the payoff. The idea is that time exists on 3 different levels. At the very top, the global level, reality is timeless, just like that equation says. But then you zoom in into a coherent chunk inside that universe, and an internal, reversible sense of time can emerge. And then you zoom in even further to our messy, chaotic local level, and that's where decoherence finally creates the one-way arrow of time that we all experience.
And that brings us completely full circle. That timeless Wheeler-DeWitt wave function, the one for the whole universe, that is the ultimate constraint. That's the lambda layer from Cret. It is the final foundational sheet music that keeps the entire cosmic orchestra playing in tune, allowing for the resonance loop that builds space, gravity, and even the illusion of time itself. Which leaves us with one last, absolutely mind-melting thought to chew on. If the entire story of our universe, the past, the present, and the future, is described by one single, timeless set of rules, does that mean everything that has ever happened, or ever will happen, is in some sense already written?